Welcome to Chapter 3. We're going to start talking about differentiation, and this is a large concept in calculus. We're going to start with the basics. We're going to talk about what is a derivative. How do we define it? This video will give you some definition, some of the conceptual background of what a derivative means, as well as some problems involving taking derivatives. So, as we talked about when we did the calculator activity, there's really a couple fundamental questions that the concept of a derivative helps us answer. And that is, what is a tangent line to a curve? And how can we compute the slope of said tangent line? Now, in order to answer these questions, because as I showed you in class, if you have a curve, I don't really know what the tangent line is that goes through that point. Is it this one? Is it that one? I mean, they're all lines that go through the curve at just the one point. There needs to be some tangent line, the definitive one. So to answer that question, we've got to go back to basically how we started the course, and that is looking at these secant lines. Okay, so this is what I got from your book. So if you look at this first picture, you've got 2 points, point P and point Q. And we can get the slope of this blue line by just taking the rise, which is our f of x minus f of a, delta f, however you want to describe it, the change in the y coordinates, divided by the change in x coordinates over x minus a, and that would get you your slope. But if we bring this point Q and we move it closer and closer to P, all of a sudden, look what the line gets. We end up getting this one true tangent line. So that's really what we end up defining the tangent line. I have a little animation that I'm going to show you next, which really drives this message home. Okay, so this is an animation here of really talking about what we mean as far as turning secant lines into tangent lines. So notice you've got that fixed point, P, which is at 2, 4. And notice that I'm taking this point Q, and I'm moving it closer and closer to P. Now, what I like about this animation is it's dynamic. So it's always keeping a line segment between P and Q, the secant line. And notice what happens as Q moves closer and closer and closer to x equals 2 and the point P. That secant line starts to become a tangent line, which is what that yellow line always is. So the yellow represents the tangent line that goes through just point P. And as we bring Q closer to P, all the secant lines start to get closer and closer to the tangent. So this is kind of an intuitive graphical idea of what we mean by trying to figure out what is a line tangent to a curve and what is its slope. All right, now we need to talk about how we define the derivative. And we define it using these ideas of difference quotients. Remember, we looked at 3 of them in the calculator lab. So based on these pictures here, there's a couple different difference quotients we can write. Remember, the idea of a difference quotient is it's the change in the y over the change in x. So using the first picture, one example we could write is the change in y is f of x minus f of a all over x minus a, which is our delta x. A second type of difference quotient that you see is more like the one we used on the calculator, where we use this distance from P to Q, the horizontal distance, we call it h. Now, our slope would be, of the secant, f of a plus h minus f of a, all over just plain old h. The change in the y again, f of a plus h minus f of a, over the change in x, which would just be h. Now, when we take the limit of these difference quotients, as you saw in that animation, when we move Q closer and closer to P, essentially what we're doing is we're getting what's happening to these secant lines as this delta x approaches 0, or as the h approaches 0. And when you put that in limit notation like we have here, what you get is the derivative. So here is one definition of our derivative. Okay? The derivative at a point A is the slope of the line that is tangent to f of x at A. And you get that slope by taking the limit as x approaches A of the difference quotient, f of x minus f of A, all over x minus a. This is huge. Put this in your notes. Put this on a note card. We need this definition down. So there we go. I just took it now from your textbook. This is exactly what I just said verbally. I have it written down here for you so you can copy it in your notes. So we say that the derivative of f of x at x equals a is just the limit of the difference quotients as the distance from point A to point A plus h approaches 0. Okay, equivalently, if we use that first difference quotient that we had here, we could also take this difference quotient and just look at the limit as x approaches a of f of x minus f of a over x minus a. Graphically, it means the same thing. We're just pulling this point here closer to the point we're trying to take a derivative of. And here that is written a little bit nicer right here. Okay, understand both forms. I would put them both on flashcards. They like to test these both on the AP. Okay, sometimes they put, and we'll do examples of these in class, they'll put what looks like a limit multiplication question, or limit multiple choice question on the multiple choice section. And really what they're just asking is computing a derivative, being able to pull out the right function that you're taking the derivative of and then differentiating it. That's all they'll be asking. But this kind of form of the problem throws students for a loop because they think they have to plug in a limit, but you really don't. Okay, another key word to look at, and we talked about it earlier in the year, and now it's coming up. When this limit, either this limit or that limit exists, we say that f of x is differentiable at the point A. In other words, you can take a derivative at that point. So that means if we're asked to find a tangent line through a point, if the function is differentiable at that point A, the tangent line is just the line that goes through a comma f of a, right here, there's your point, that has slope f prime a. And as we know, if you have a point and you have a slope, you can write your equation using point-slope form. All right, and there it is. It's y minus y1, which in this case is f of a, equals your slope, which we now are calling m, times the quantity x minus x1, which we're now using as x minus a. Just basically think of this as the point slope you learned about in Algebra 1 in pre-calc, but instead of, Algebra 2 in pre-calc, but instead of x1 comma y1, we're using a and f of a. That's all it is. It's just different letters. Okay, so let's do some examples. Let's find the equation of the line tangent to f of x equals x squared at x equals 4. All right, so first thing we got to do is we got to get the slope of the tangent line. So we need f prime of 4. And as we said, that's the limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. All right, we have to evaluate some functions at different values. So f of 4 plus h will be 4 plus h quantity squared. F of 4 is just a number. It's 4 squared, which is 16. And h is h. And I should really keep this limit because I have not evaluated the limit yet. I've just rewritten the numerator. Now, let's expand the quantity of 4 plus h squared to get me 16 plus 8h plus h squared minus 16 all over h. Okay. Now, if you try to go and evaluate h for 0, you're going to end up with a 0 over 0 situation. You could have noticed that from the get-go. You would have f of 4 minus f of 4 over h. And that's going to get you a 0 over 0 situation. So now what we have to do, is try to simplify the top. Well, I've got a 16 and a negative 16, so I'll cancel those out. Now I have the limit as h goes to 0 of 8h plus h squared all over h. Look what else I can do. I see an h in both terms of my numerator, so why don't I factor them out and do the limit as h approaches 0 of h times the quantity 8 plus h all over h. And now I can cancel out this h, which basically gets rid of my 0 over 0 situation. The limit as h approaches 0 of 8 plus h is just 8 plus 0, or 8. So right there, that is f prime of 4. That is the slope of the line tangent to f of x equals x squared at x equals 4. Now, to actually get the equation, we're just going to use our point slope. So we do y minus y1, and in this case that is f of 4, which is 16, equals the slope 8 times the quantity x minus 4. And you can stop there. On the AP test, especially the open-ended, if they ask you to write a tangent lines equation, you can stop and leave it at point-slope form. If you want to get cute and distribute and put it in slope-intercept because you're used to that, you can trust me on the algebra to save some time in my video. I'll just tell you that it converts to y equals 8x minus 16. Okay, let's do another one. Let's do one that's a little bit more of a complicated function. Let's use x squared minus 3x, and let's get just the slope. Let's get f prime of 2. We don't have to turn it into the actual tangent line. Let's just get what the slope of that tangent line would be. So again, we'll use our definition of the derivative, f prime of 2. It's going to be the limit as h approaches 0, of f of 2 plus h minus f of 2 all over h. Okay, we're going to take this 2 plus h and replace it for both x's in this function. So now I get the limit as h approaches 0 of 2 plus h quantity squared minus 3 quantity 2 plus h. And then I'm going to subtract that f of 2. So when x is at 2, I get 4 minus 6, which is negative 2. So I get minus negative 2 all over h. Let's turn that minus negative into plus 2. Now we want to start to expand our parentheses. So the limit as h approaches 0 of 4 plus 4h plus h squared minus 6 minus 3h plus 2 all over h. Okay, so let's do some cleanup. I've got a positive 4, a positive 2, and a negative 6, so let's cancel all that out. Now I have a 4h and a negative 3h, so we'll combine those to get the limit as h approaches 0 of h squared plus h all over h. Okay, I can factor out an h, cancel it, and I get the limit as h approaches 0 of h plus 1, which then would be 1. So that is f prime of 2, the slope of the line, tangent to x squared minus 3x at x equals 2. All right, now let's look at a graphical example of what's going on. I took this one right from your book because I want to just talk a little bit more about the graphic representation of a derivative. So sketch the graph of f of x equals 1 over x and its tangent line at 2. All right, so let's do that first. Okay, so 1 over x is the reciprocal function. It's got both a horizontal asymptote at the x-axis and a vertical asymptote at the y-axis. We know that there's the point 1, 1 right here, because 1 over 1 gets you the 1. And then I'll eyeball 2 to be about right there. So I want the line tangent to the red graph at 2, so that's about that. Now, let's do the first question here. Based on the sketch, do you expect f prime of 2 to be positive or negative? Well, look at the black line. The black line, as you read from left to right, is going downhill. So yeah, I definitely expect this to be negative based on the line that I drew tangent to the curve at 2. It has a negative slope. And f prime of 2 just represents the slope of this line. So that should be negative. Now let's actually find it. Let's get the equation for the tangent line at x equals 2. This is a good one because the algebra on this one is a little messy, so I want to make sure we understand it so when you do something like this on your own for the homework. So I want the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. So we're trying to get the derivative at 2 first. So that's going to be the limit as h approaches 0 of 1 over 2 plus h minus 1 over 2 all over h. This is why we did weird limits like this in Chapter 2, so that you could handle this. Okay, we've done ones like this before, where I've got a complex fraction. My first step is to get common denominators so that I can subtract these two fractions. So if I multiply the left fraction by 2 over 2, and the right fraction by 2 plus h over 2 plus h, now what I get is I'm going to get my limit as h approaches 0 of 2 minus the quantity 2 plus h all over 2 times 2 plus h all divided by h. Fraction over fraction means I can rewrite this. Limit as h approaches infinity. Well, if I distribute my negative sign, I get 2 minus 2, which cancels, and then a minus h over 2 plus h. Then dividing by h is like multiplying by 1 over h. Oh, look, the h's cancel. So now I just have the limit as h approaches 0 of negative 1 over 2, quantity 2 plus h. When I stick the 0 in for h, I'm going to get negative 1/4. So that's the slope. Hey, look, that just verified numerically what I said in the first question. I knew we would have a negative f prime of 2 because of the picture. And I've just proven it with algebra. Now to get our equation for our tangent line, we can actually just use that slope. So it's going to be y minus 1/2 equals negative 1/4 x minus 2, using my given point and my slope. Now, are you going to have to do this limit definition for every single derivative? No, but you have to be comfortable with it. You know I'm going to test you on it and quiz you on it. But let's start looking at some shortcuts. This is Theorem 1 in page 123 of your book. So they gave you two shortcuts. If you have a linear function, f of x equals mx plus b, well then f prime of a is just going to be the slope of that line for all a. Okay? Because think about it. All your secant lines, if you have just a plain linear graph, and you pick 2 points on the line to draw a secant, well, what slope are you getting? You're getting the slope of the original line. And if you take this point and bring it closer to that point, all the secants are still going to have slope m. So it makes sense that the derivative of a linear function should be just the slope of that linear function. Same thing with this second theorem. So if f of x equals b, then f prime of a equals 0 for all a. So if we have a constant function b, here it is, and I want to take the derivative at a, okay, think about this idea of secant lines becoming tangent lines. Well, I start here. What's the slope of this line? Well, it's a horizontal secant, so it's got to be 0. I go closer, it's still horizontal. Slope of 0. That must mean the limit as I take this point and I bring it closer to a has to still be slope 0. So, if you have a constant function, its derivative must be 0. Okay? I think I've given you enough to chew on here. Watch the video again if you need to. Rewatch some of the algebraic examples. But I think for the most part, this should help you when you do your assignment for 3-1. If you have any questions, feel free to email me. Be sure to ask about them in class. And with that, happy differentiating.